first, we will review a classical diagram of a neural network. So neural networks have been in the literature for more than 20 years, at least 40 years, I think. Here what we will do is we'll take this image and we will use an operation called flatten so that it can be processed by our artificial neural network. So this is the pre-processing operation here. So to flatten this image to a vector, so here we have our local representation, and the local representation would be in a vector, and here I have an image that is a tensor, that is something that has 3 dimensions, the height, the width, and the number of channels. So to flatten this image, I will fix an order to iterate over the pixel intensities. Like I can iterate column by, no, here I'm iterating row by row. And so the first unit of my model will be pixel at position 1, 1, the red channel, the green channel, the blue channel. And then I go down 1 step, and I will retrieve the pixel intensity of the red channel of this pixel here, etc. So I do a flatten. I retrieve my vector for this image. And in fact, you should not do it with modern deep learning. It's only to show you the modular approach. Now we have operation that will preserve the structure of the image. By doing so, we lose what are the pixels that are the neighbors to a given pixels. Because I take a 3-dimensional object and I transform it into a 1-dimensional object. But it's only for this example. So these are my local representations. And now we'll implement this idea of feature extraction on it. So my image is fully represented here, pixel by pixel, channel by channel. And I will create this one node here. It will be called an artificial neuron. And I will create my first hidden layer here. And this artificial neuron will receive the values of the input through these connections. And for all connections, I have one parameter, W from input 1 to hidden neuron 1. And here it's from input 3 to hidden neuron 1. So what this diagram represents? If I have a node, a processing unit here, a connection, and a parameter here, it means that I'm multiplying x1 with w11. So I'm doing the product of these 2 values. Here I have multiple connections going in this neuron, and what it means is that I'm summing the product of all the connection with the input. So it's the sum over the product of all these parameters with all the neurons here. And this is a scalar product. This is exactly the definition of a scalar product. So as you can see, the parameters here will encode the pattern. This will encode the data. And now this neuron will compare will contain the value that represent the product of this parameter with this, and the sum over everything. And after that, I still need one operation called the activation function. So the activation function can be a sigmoid, a tanh, or a rectified linear. These 2 have been used by the community for years. This one is more recent, from 2010, and this one works better than the 2 others on many data sets. And we'll see a little bit why. It's because these 2 are more hard to train. So the full equation is, for this neuron, I have the activation function, and the activation function will take the scalar product. Again, the product of the parameters with the input, and the sum over everything. So this is one pattern. If I want to define multiple patterns, I just have to add other hidden units. So now one hidden unit is associated to one pattern. And so this is the general equation. For the neuron yj, I will receive the activation function applied to the scalar product of the input and the connection drawing to the neuron j. And this is a new representation for my data on this layer. And it's called a distributed representation. It's distributed because the scalar product will mix all the dimension of the input vector together. So if I add like the width of the petal and the height of the petal, the width of the sepal and the height of the sepal, then for this neuron, everything are mixed together, and we call them distributed representation. It's hard to interpret because we can say it's 0.1 the first feature plus 0.5 the second feature plus minus something the third feature, and then I have an activation function. And to really interpret what this neuron encode, it's something that is hard. And that's why many of the models are not interpretable. When we look at the representation learned inside the model, it can be hard to interpret. And since we have a new representation, we can consider this layer as new features that have been extracted from the previous layer. And I build a new hidden layer with 2 new artificial neurons. And again, they will do the same thing. They will extract patterns from this layer. And at the end, I have only one neuron to predict, as an example, if it's a chair or not, by combining these 2 values. So this is a multi-layer perceptron. It's one of the most famous artificial neural networks. And the classical diagram of it, how to represent the operation done by this model. So one question that we can ask ourselves is, do we really need activation functions? Instead of using these 3 functions here, why not just using a scalar product? And in fact, if we just use scalar product, this corresponds to a linear transformation. It's like I'm doing the product of a matrix with a vector. And if I'm doing several linear transformations composed together, the complexity of it, it's only one linear transformation. By composing several linear transformations, I don't gain anything in complexity. By using activation function, I'm adding non-linearities in the transformation. I cannot express my multi-layer perceptron only as one transformation because of this non-linearity. So they are important to increase the complexity of the model. Another way to increase the complexity is to add only more layers, more and more layers in the network. The representation will become more and more abstract, and at the end, we hope that the classifier that will separate the classes will work on a space where the representation are very well organized, and only a linear separator will do the work at the end of the network. Also, there are theoretical results about the universal approximation theorem. This theorem only says that by using this kind of activation function, and I think there is a new one with the ReLU, we can approximate any continuous function if we are using enough neuron on the hidden layer. And so it's good to know that the complexity of this model, with the complexity of this model, I can approximate any continuous function in n dimension. But in fact, there are this theorem, the universal approximation theorem, was about only one hidden layer. And so with one hidden layer and a sufficient number of hidden neurons, we were able to approximate any function. And so people were asking, why do you want to have more hidden layers? Because we have this theoretical result. It says that one hidden layer is enough to approximate anything. Why do we need deep neural network? And it's only about the representation power of the model. Having several layers with activation function, it's easier to learn from the data. And this theorem only describe what the model can approximate, but is it hard to learn or not? This theorem will not answer this question. So there's a difference between what we can approximate and how easy it is to learn it from the data. And now, empirically, we know that using deep neural network, it's easier to learn from complex data. But still, we keep this, with deep neural network, of course, this theorem still holds. We can approximate many, many functions that are interesting. Activation functions can also modulate the representation. So let's say my representation vary from -10 to 10 or -100 to 100. With a sigmoid function, I can bring the range of my representation between 0 and 1, or with the tanh between -1 and 1. So it's a way to restrict the range of variation of my representation in the graph.